everyone. I hope you had a good break. Then let's now resume the 3 last lectures of the course. We're going to do a bit of uncertainty estimation and then wrap up the course. And of course, there is an exam afterwards. Yeah. So some of the announcements today. So there is going to be is that exercise 2? Yes, that's going to be exercise 2. Yeah. There's a recap session after the lecture today by Evgeny. I have a few kind of items to share for exam. The date has been there. I have opened the registration, so the link is on Discord. So please follow the link, and if you wish to take the exam, just write down your name and so on. You have access to past exam papers, right? I guess you're all in Discord, so we can take a look at that. There's a bit of change in format for the exam, so I wish to kind of briefly talk about that. Last year, there has been 6 easy questions and 3 hard questions, and you're recommended to choose one of the hard questions. But now, this year, we're going to have 6 easy questions and 3 medium-level questions, and the advice is to attempt all of them. Because last year, it was kind of unclear whether people should actually try out all these questions or not, so we made it a little bit clearer this year, okay? So here are some information. The registration deadline is Thursday before the exam to give us time to kind of know how many exam papers we need to print, basically. So please indicate which one you are taking before this deadline. And now let's move on to the lecture, okay? So we didn't get to finish the definition and evaluation part last time. So for that, I wish to kind of briefly recap what we talked about a month ago. So we talked about epistemic versus aleatoric uncertainty. So if you have overlapping kind of labels in some region in the space, then we say that's aleatoric uncertainty. When you have a region where you do not have any coverage from your training data, then that's epistemic uncertainty. Yeah. And we talked about proper scoring rule as well as kind of reward for encouraging the confidence reporting to kind of follow the actual probability of getting something right, okay? So we say that a function is a proper scoring rule when the expected value under the true distribution is maximized only when well, actually, if and only if when the reported probability is actually the probability of success, okay? And now we also said log scoring rule is an instance of proper scoring because the expected reward is maximized if and only if the reported probability is equal to the true probability. And then we had an observation that, well, actually to provide a proper scoring loss function for your network for binary cross entropy, so for binary classification problem, you don't actually need to change anything. You can just continue using binary cross entropy loss function for training the model, because that's actually also encouraging the model to predict give you the right level of confidence when the confidence is given by the max probability, okay? We also looked into calibration and a related measure of expected calibration error, where the requirement is to make sure that the model is predicting the right level of confidence, which is equal to the probability of getting that sample equal to the kind of frequentist definition of if I try to solve this problem multiple times, how many times am I going to get it right? To do that, you have to bin the samples according to the predicted confidence level first. And then within that bin, you're going to measure the accuracy and compare that accuracy against your reported confidence level and try to see what is the difference between the two. Okay, and let's continue from this point and ask ourselves whether we need this precise reporting of the true bin-wise accuracy. That is what is required by calibration. You really need C of X, the confidence level, to give you the probability of getting that sample right. But there's a weaker condition than that. When you have multiple samples, you're going to have different probabilities of getting each sample right or wrong, right? Here, what we are saying is we only need the right ranking of samples given by the confidence. So if we rank all the samples according to confidence level reported, we just require the topmost ranking samples to be correct and bottommost samples to be incorrect. And that's weaker than calibration, which is kind of requiring you to get all these confidence values right. And potentially conceptually simpler, and also evaluation code is simpler. It doesn't depend on the binning and approximation of the frequentist probability and so on. So this weak ranking condition is much easier in practice. So this is what I mean by that. So in ranking evaluation, you care about two quantities for every sample: your confidence level predicted by the model, as well as the binary signal of whether you got the sample right or wrong. In general, you wish the high confidence sample to be right and vice versa. In other words, this is like a solving binary detection task. So given the feature which is given by the model's confidence level, you wish to detect samples that are correctly predicted by the model. And since this is a binary detection task, you have natural notion of precision recall, true positive rate, and so on. So I'm going to go over some of the basic kind of evaluation techniques here. So now we are given a vector of confidence level, C, and a vector of correctness, binary vector, right, L. And I'm going to plot that in 2D space with Ci on the x-axis and Li on the y-axis. And the green here means you got these samples right, and so L is 1, and red means you got it wrong. And in general, you see that, for the samples with lower confidence values, you got it wrong, and vice versa, which is good. And based on this, we can now define true positive, true negative, and false negative for each threshold t. So when we set the threshold t here, then the positives, meaning the Li is 1, for which the confidence scores are also higher than t, these are called true positives. I think these are kind of obvious from the drawing here. And based on this quantity, we can compute a lot of metrics here, like precision and recall. Precision is basically the ratio of these points divided by the green points here and red points here. So among the positive predictions according to threshold t, how many of them are actually positives, right? And in this case, we get 85% precision. And recall is basically among the actual positive samples, how many of them do I predict as positive, right? And that value here is 92%. So when t is here, then we say we have a good balance between the precision and recall. Of course, when we have, t is still here, but t is here, right, for example, then we get, when t is higher, then we are kind of becoming more and more conservative about what do we consider as positive. And so your precision will remain very high or get even higher, but your recall is going to be lower. And vice versa, when your t is lower, then you're way too relaxed about what do you consider as positive. And so your precision will get lower, but you're retrieving much more samples. And so your recall will get higher. This is too forgiving. So here the problem is that for infinite values of t, you can get quantities like precision and recall. So how do we make a final number that's going to tell us whether this model is doing a good job at detecting correct samples? For that, people look into area under curve, right? So we plot precision and recall curve, like here. And of course, for the perfect classifier, you're going to keep the precision as high as possible until you recall every item as you lower the threshold, right? And so if you compute the area under curve for precision recall curve, you're going to have 1. But in general, you're going to have drops in performances as you lower the t, because you're also going to reject some of the true samples and accept some of the false samples, right? And the baseline classifier is the one that has no idea what it's doing. It's just randomly assigning correct samples and incorrect samples with random confidence values. And in general, for this kind of baseline classifier, your precision level will remain at the level of the ratio of positive samples in the data set. Okay, so if the ratio of positives are, I would say 90%, then your baseline classifier will be at 90%. So here is the caveat, which is for imbalanced test set, your random classifier, which has no idea what it's doing, will still get 99% area under precision recall curve, AUPR. And so it can be misleading. You can just look at the number and say, yeah, it's actually doing a good job. So we need some kind of a different metric maybe, which is immune from this problem. And so people make use of another metric, which is TPR versus FPR, true positive rate and false positive rate. True positive rate is actually exactly recall. False positive rate is different from what we have seen so far. It's the ratio of false positives among the true negatives. Sorry, actual negatives in the data set. Okay. So in terms of the plot here, that's going to, so true positive rate will be the ratio of these green samples beyond threshold t among all the green samples. And false positive rate will be the ratio of these red samples beyond threshold t among all the red samples. Okay. And if you measure these two, you can also plot this, it's called now ROC curve. And you can measure the area under ROC curve. It's called AUROC, AUROC, right? And in this case, again, the perfect detector will have 100%. A random classifier, regardless of how much positive samples we have, it's always going to be 0.5. Okay, so it's, I would say, better calibrated measure of how well you're detecting. So that was the quick recap for evaluation metric. I guess you're pretty much familiar with these concepts. Yes, and people report, like in those kind of papers, the AUPR or AUC or AUROC. I think AUC is exactly AUROC, to indicate how well the predictive uncertainty is doing its job. Okay. So we looked into evaluation of C of X as predicting how well it's predicting it's going to be wrong. But now we can also take a look at that from the perspective of detecting something related but slightly different. We may also use the quantity for detecting out-of-distribution samples. Like for out-of-distribution samples, you're also likely to get it wrong, right? But it's not always the case. You may still get them right, and you may still find in-distribution samples harder and get it wrong more frequently. So it's kind of an independent question. Like it's related, but still a different question. And for detecting this kind of ODness, or the other case is whether the sample is corrupted, which is more related to aleatoric uncertainty question, or whether the sample admits multiple answers. To answer all these questions, you can also set the target not just for detecting correctness of the prediction, but also oddness or multiplicity of the labels for the sample. Okay, so all of that is possible, and people do it quite frequently for OD detection as well. Yeah, so if sample is outside a training distribution, you put L equals to 1 and vice versa. And here again, you can measure AUPR or ROC measures. So that's it for the evaluation part. Summary goes like, yeah, there's proper scoring rule, log likelihoods, prior scores. We also looked into calibration and ranking-based evaluation today. For epistemic uncertainty, you can take a look at OD detection measures like OROC or AUPR. For aleatoric uncertainty, you may also use multiplicity detection, although I haven't seen that quite a lot in the literature. But that's a possibility. Okay, so I guess if there's no questions so far, I can move on to the next section. Okay. Now, let's talk about epistemic uncertainty. It arises when there are multiple possible solutions given the training set. Okay. Some possibilities are when the training data is way too small and the training distribution is not covering all the relevant spaces in the input space. And Bayesian machine learning lets you train multiple models at the same time that fits to the training data well. And if there's a kind of diversity in the models that admits the training data, in other words, a diverse set of models with low training loss, then that's a good indication that those models are not agreeing on a certain region in the input space, and those spaces are likely to be OD, which is different from the input distribution. Okay, so even after observing all this data, if your posterior theta is kind of diverse, yeah, then that's a nice situation where you can detect the ODs. You can think of Bayesian machine learning as kind of reducing your hypothesis space into a smaller region as you train with more and more training data. But of course, if your training data is small or not covering some space, then you're not reducing your posterior distribution in the parameter space all the way down to the relevant model. And you still have quite some multiplicity in the model. It's also called underspecification, that the data is not telling you perfectly what is the right model that you're looking for. So let's talk a little bit about posterior. So posterior is the kind of the container which tells you what are the possible solutions for the model. In the most general case, we have very complex posterior as well, like this one here. It's even 1D, but I would say it still has quite a bit of degrees of freedom. There are 1, 2, 3, 4, 5, 6, 7 modes, and that means you have to at least encode 7 different points where the modes are, and each mode seems to have different width, right? So such a mixture, multimodal distribution admits much more degrees of freedom than the number of dimensions there is, which is 1. So depending on how much freedom you're giving to the posterior, you can encode quite a lot. But of course, when you are only considering simple distributions like unimodal Gaussian, you just need two parameters here to encode it, right? The mean and variance. So yeah, and of course there's also sum of Dirac's distribution to kind of encode possible weights, parameters in the space. And here the degree of freedom is exactly the number of Diracs you put in the space. As a special case, you can also have a single Dirac as the posterior. And that's exactly the case when you have deterministic neural network. So everything that we see here is a generalization of deterministic neural network. So maybe it's a little confusing why I talk about all of these posteriors and so on. I hope it will get clearer as I go further. But what to remember here for now is that probability distribution and kind of posterior modeling is a very versatile tool for encoding multiple networks at the same time. If you admit more degrees of freedom, then you can kind of store a lot of models in this distribution, potentially infinite number of models. If you're reducing it all the way down to single Dirac, then you're coming back to the original deterministic neural network, which encodes just one model. So Bayesian neural network, which is needed for epistemic uncertainty estimation, is essentially training an infinite number of models or a set of models, which may be an infinite space, continuous space, or discrete infinite. In any case, it's a set of models that you're training. Comparison against deterministic machine learning. In deterministic machine learning, you just care about a single model. But now in Bayesian machine learning, you care about a set of models. And once you train a set of models, which is encoded by this probability distribution in the parameter space, what you do at test time is just combine the predictions from this set of models altogether by doing some average across all these predictions for every model. So these are individual predictions from every model in the distribution, and this is the likelihood of every model in the distribution. And then you're summing over them, so it's weighted average. It's called Bayesian model averaging, EMA. Sorry, I didn't put the name here. Bayesian model averaging. So perhaps the simplest way is just to train n different models independently, right? Which can be expressed as a sum of Diracs, like here. And we call them ensemble, right? You just get an ensemble. You train m different models and then average the outputs. How you do that, right? You just select different random seeds for training multiple models, and you just train them independently. And because the model, the training landscape, the loss function is highly non-convex for deep neural networks, depending on where you start, you're going to end up in different basin of convergence, and therefore different local minima. And so that kind of ensures that your set of models are kind of diverse for deep neural networks. If it's a convex function, regardless of where you start, you're still going to have very similar solutions. But this is deep neural network. And after training these M models, what you do with Bayesian model averaging is you just take the average of them. So we saw that we can express this procedure as a Bayesian model averaging over the posterior distribution. And if we plug in the sum of Diracs here, right, you can just pull these summation and scalar factor out. And then you realize, yeah, the delta here and the summation here can get canceled out by just replacing the thetas with theta m. It's very similar to the multivariate calculus that we did as well, right? You can remove the integration and the Dirac together by replacing theta with theta m. And so eventually you just have theta m here, and then you're averaging the predictions from individual models here. Okay. So once you have So let's say the theta 1, 2, and 3 here are three different differently initialized solutions for the neural network. What you're going to have for as the Bayesian model averaging for the sample in this triangle region is you're more or less going to have a similar prediction for every member of the ensemble. And therefore, the prediction for the class, the predicted class, a triangle, will be close to 99% for every model here. And so the average of them will still be 99%. But for this sample here, the ensemble of models will produce different labels. And so let's say the max probability for this sample will be 59%, which is quite low because the max probability can should at least be 50%. So it's only 9% point above the random chance or the worst case. So you know, like I went through the deep ensemble now as kind of casually as one possibility of doing it, right? Doing the Bayesian model neural network. But actually, there's a paper around this, right? Which was accepted at NeurIPS 2017. So it's a very simple idea, but still, Bayesian machine learning people, they managed to get these simple ideas out by putting some equations there and you know, like giving some insights and making arguments. Yeah, this is still Bayesian machine learning, but you know, like in practice, it's not so different from what you're actually doing. So these kind of arguments are very typical in Bayesian machine learning community. It's really interesting. So what's shown here is, first of all, the classification error, right, of the ensemble of models, and negative log likelihood, which is encoding the predictive uncertainty, right? And Brier score as well. That's kind of encoding how good your your predictive uncertainty is. Unfortunately, there's no measure that's designed specifically for OD detection, but still, it kind of shows that if you look at the ensemble here, red curve, you see that yeah, classification error is good. Negative log likelihood on the test samples is also good. Brier score is also good. Although, yeah, with some additional techniques like R, I don't actually remember what R stands for here anymore. AT is adversarial training. With these techniques, you get even better performances here, even better than Monte Carlo dropout, which is yeah, another method that I'm going to talk about later on. So they are basically saying it works in practice. Actually, this is the results for OD detection. So they did the experiment of MNIST versus not MNIST data set, where MNIST is the digits and not MNIST is similar kind of black and white images, but not digits. Okay. And if you look at the entropy values for the ensemble, so 1, 5, 10 means how many members there are in the ensemble. For in-distribution, regardless of how many members you have in the ensemble, you're going to have a high peak in the low entropy values in the prediction. So that means in-distribution samples are considered with high confidence, right? But for out-of-distribution samples, as you increase the number of ensemble members, you're going to have higher entropy values for the prediction, for the Bayesian model average. That means the entropy value, which is now the C of x in this case, is a good measure for detecting ODness. Okay. Yeah, so the only point here is that they also did some experiments on ImageNet, which is much bigger scale than MNIST. And it kind of works here in terms of error, as well as negative log likelihood and Brier score. Some pros and cons. Pros, it's conceptually simple. You can just continue doing what you have been doing, right? A lot of people use ensemble method. You can just keep doing that. If you consider this from practical point of view, you can do ensemble for any kind of model, right? You can do this for linear regression or even large language models. It's embarrassingly parallel. You don't have to change the training code at all. You just need to find a few more GPUs to run the models. Yeah, you can still have a single GPU and do this, right? You just wait until your current run is done and then you do the next run. The downside of this is that it's kind of simpler and it does not realize the full potential of Bayesian machine learning, which is in the promise of training a infinite set of models. And space-time complexity is kind of scaling in a dumb way. It's linear in number of models. So let's move on to training actually an infinite number of models. This is possible when the posterior is a continuous distribution. We can encode infinite possibility of the models by only with the finite number of parameters by using continuous distribution again. So here, in this case, we can assume that the true posterior is kind of close to a Gaussian distribution in the parameter space. So there is a mean mu and some covariance matrix, sigma. Yeah. The problem is that this assumption will be wrong in practice, of course, right? Because the solution space will not look like a Gaussian at all, right? And also the solution space, like for deep learning, you have multiple local minima, right? So at least you need some multimodal distribution to encode solutions, yeah? So if you're confining yourself to a single Gaussian, then you're missing out a lot. But still, you can do something like, yeah, we know we are wrong, but we are kind of choosing the least wrong answer in this assumption, right? So what you can do is you can try to minimize the distance between your predicted posterior versus the true posterior by minimizing some distance measure between these two random distributions. Now, we're going to follow the methodology introduced by Bayes by Backprop paper, which is from 2015, quite old paper. And they chose KL divergence as the term here to compare the two distributions. And then by expanding the KL divergence term here with some steps, eventually you get some kind of loss function, which is supposed to give you a good loss function for training an infinite number of models. So I'm going to go over each step here one by one. So again, you're measuring the KL divergence between the Gaussian and your true posterior, which is unknown. So eventually you wish to minimize this, right? Because you want the KL divergence to be as small as possible between your prediction and the true posterior. Just keep that in mind. And you probably remember that KL of P and Q is P log P over Q integrated. And now you can apply the Bayes theorem to kind of express the posterior in terms of something that you can kind of handle better, which are basically the likelihood and the prior. Okay, so like posterior is proportional to likelihood times prior, right? And there's a C, which is the factor that dictates how proportional the linear relationship between the two. So far so good. No exotic ingredients. you're now expanding the logarithm here for the prior and the likelihood. Okay. And here the trick is that you can, no, there's no big trick. You just do it. Yeah. And then if you look at the left, the first term, it's actually KL divergence between your prediction and the prior. Okay. So you can just write it down like this, right? For prior, you actually have full control over what your belief is, right? So you can even say this is a very simple distribution, and then you can later on use this as a loss function. What is more important is the second term, which is kind of a different way of writing the expectation now, right? So you're now sampling the theta from this predicted distribution, and then you're measuring the log likelihood of the data points based on that distribution. Sorry, based on that sample from the predicted distribution. And now you can write down the data term, the likelihood term, in terms of the products of individual data point likelihood, right? Because you assume that the data is sampled IID, right? So the probability for the data set is essentially the product of individual likelihoods. And the product becomes a summation, because there's log here, and you can write it down like this. And finally, to compute this or to estimate the expectation here, you're taking k samples from this predicted distribution, and then plugging in that sample into the computation of the main term here, and you're averaging afterwards. Okay, so there's no like super complicated magic here. There's not even Jensen's inequality here. You just expand everything, and eventually you get this KL term plus some data term, the log likelihood term. Yeah. So that's it. That's your formulation. And now the question is how to make this DNN friendly. Let's take a look at the first term here. It's telling you that your prediction should not be too much different from some prior. A popular choice for prior in Bayesian machine learning is just unit Gaussian. 0, 1, sorry, so 0 is the centroid, and 1 is the isotropic Gaussian, basically. And for my prediction, I'm gonna parameterize this by a vector mu, which has the same dimension as the sig theta, the parameter space. And sigma here will be a diagonal matrix. I'm still assuming an axis-aligned Gaussian and not kind of skewed Gaussian in the space. If you allow for skewed Gaussian, then you're introducing n times n minus 1 over 2 more degrees of freedom. And that's way too much in parameter space. It's millions of points. If you admit quadratic number of degrees freedom, then it's going to be a very difficult optimization problem anyway. So a popular choice here is either an isotropic Gaussian with a single degree of freedom, or one uncertainty factor per axis. So you have the same degree of freedom as the parameter space dimensionality. If you choose these ingredients, then the KL term here is essentially the KL divergence between the predicted Gaussian and prior. And this boils down to a very simple formula like this one here. Okay. So that's like a regularization term for your mu and sigma. The second term is essentially the data term, right? So this is a kind of typical regularization with data optimization. If you look closely, this is just a cross entropy loss. If the likelihood is dictated by the cross entropy, the log likelihood is cross entropy classification problem. But the only difference is that the sigma here is now a Monte Carlo sample from the predicted distribution. So the aim here is not to train theta, as in deterministic neural network. Your aim is to train mu and sigma instead. How can you do that? We can use reparameterization trick, which is essentially writing down the sigma here as a sum and product between the parameters involved, mu and sigma, and some random factor, epsilon, where epsilon is now sampled from a unique Gaussian distribution without any parameter. So what we did here is essentially separating the randomness and parameters, the backpropagation. So we know how to get backpropagation, the gradient for theta. In deep learning, we just use backpropagation through all the layers, and we're going to get gradient for theta. Now the question is how to get the gradient for mu and sigma based on the gradient for theta. The answer is to use chain rule. Right? So given this fact, the chain rule simply gives you that the gradient for mu is essentially the summation over different elements of theta, and then theta should be derived against mu I. And you know, like when you derive mu with respect to theta, that's essentially an identity matrix. So the gradient is actually the same for mu and sigma. For sigma, the only difference is that you're going to have a factor here, which is multiplied on top, which is essentially a sample from this noise distribution, unique Gaussian. So you can do the gradient descent for mu and sigma almost in the same way as you do gradient descent for theta. You just need to multiply this factor here on top of gradient to get the gradient for sigma. That's it. So it's very DNN friendly. Yeah, the other caveat here is that your thetas, so theta is a parameter, right? It has to stay positive. And in general neural network, we never care about the effective domains for the parameters and so on. We just let it be any point in the Euclidean space. But how can we put a constraint that a parameter has to be, for example, positive? For doing that, what people do is to parameterize something even more latent, rho, right? Where rho is allowed to be any value in the real line. It can be negative as well. But you put some differentiable function on top of it, which essentially makes the output of the function positive. A popular choice is soft plus, which is log of 1 plus x of the input. And this is always positive, and this is fully differentiable. The other choice is to use ReLU, of course. But I haven't seen people using ReLU a lot in this domain, although I have also seen that as well. That's a possibility. Okay, and in terms of code, it's not super complicated. That's the only point here. So this is PyTorch code. You define the mu and rho as parameters, right? Where you put some kind of initialization as uniform distribution somewhere, right? And during the forward pass, what you do is you essentially you do not directly sample from the normal distribution parameterized by mu and rho, mu and sigma, but you are first sampling from some unique Gaussian here, and then multiplying that unique Gaussian apps here with the sigma value, which is essentially the output of the soft plots of rho, and you add mu. And then you do multiplication with you compute your network function with this obtained theta, okay? So theta is now a sample from the parameter, posterior parameter. And based on that, you're computing loss, right? Based on this feature, you're now computing the logits, and afterwards, everything you do is kind of identical to how you would train a deterministic neural network. just compute the log likelihood. And there's some regularization term, which is kind of specific to Bayesian neural network. You just sum two of them and then put gradient. You don't do any chain rule explicitly here, because the neural network frameworks, they take care of that by itself, right? So you just define the parameters like this, and the neural network knows what to do for obtaining the gradients for mu and rho. So this is it. So here we went through all the formulation and all the tricks for formulating it, explained why we do this, KL diversions and so on. But the whole point I wish to make here is that essentially from practical point of view, Bayesian machine learning is very simple. It's not too different from what we are already doing in deterministic neural network. The only difference is that you're kind of sampling multiple times from the posterior prediction and averaging the outputs and backpropagating through the sampling procedure. Yeah, I feel like I'm repeating myself. So yeah, this is essentially saying, yeah, variational approximation gives you this formulation. For the likelihood, you're actually sampling multiple times from the posterior prediction. Yeah. Sometimes you need to clip the parameter values. For that, you can use softclass. Oh yeah, and then after obtaining the optimal mu and sigma, you can do Bayesian model averaging again by plugging this in. In practice, what you do is you sample a few times from this mu star and sigma star, and then get the outputs from these models and average them. That's it. So I wish to give you a simple intuition here again. So how to train a set of models and test with the set of models, right? That's essentially the essence of Bayesian machine learning. Just parameterize the posterior. During training, you sample multiple times, train with these sample weights, and you backpropagate to the posterior parameters by using reparameterization trick. After training, you trust that your posterior is representing the solution set, and you sample multiple times from the posterior, predicted posterior, to obtain the predictions, average them, and if the variance for that prediction is high, then X is likely to be an OD data. And finally, optionally, you can try to justify the steps 1 through 4 using some fancy maths as they did in Bayes by backprop. Let's continue Monte Carlo dropout. So essentially, Bayesian machine learning is you train with, well, actually before that, do you have any questions? I thought of asking this. Otherwise, I'll just move on. Okay, so Monte Carlo dropout as well. The philosophy is the same. You just train with randomness, and at test time, you use the same randomness. Okay. Do you all know dropout? Or do you? Okay. So dropout normally means you're dropping out the features, right? But here we modify the original definition and say we are dropping weights. So I remember there used to be these two different definitions of dropout. In deep learning libraries, I'm not sure if it's still there. But the effect is, I would say, essentially very similar because you're kind of reducing the connections in the neural network. So dropout means you're essentially turning off. Turning off here means you're replacing with 0, right? So you can do that on features, especially if it's a ReLU activation feature. Then 0 has a clear meaning that your feature is doesn't play a role, right? For weights as well, you can do turning off the weights as well. You can replace the weight values with 0. and you're going to have a sparser neural network. So there are different insights on why dropout is helping and so on. But here we focus more on the perspective from Bayesian machine learning. By turning on or off some of the weights, we're essentially training an infinite number of, not an infinite number actually, an exponential number of networks at the same time. Yeah, one configuration of which weights are turned on versus turned off is one model sample from some distribution, which you can express as some kind of Bernoulli or a set of Bernoulli decisions on what to turn on or what to turn off. It's actually a very weird kind of distribution. It's not a standard kind of distribution that you'd consider in probabilistic theory at all. But still, you can write down something here, and so yeah, you can still say this is some post area. So if you train with multiple possible configurations, then eventually you're trying to make sure that regardless of which weights are turned on, it's fitting the training data well. Okay, that's a very difficult thing to do, but in practice that seems to work. Regardless of which weights you turn on, they all seem to encode very good or have very low loss on the training data. That's magical, but that happens. But at test time, what people normally do is they still take a deterministic neural network by, for example, taking value p, which is the probability of turning on or off the Bernoulli random variable. You just plug that in into, or you just multiply the feature with this value to get the final output. So that used to be the original dropout implementation. But here, we make use of the infinite number of possibilities. That means we're still sampling from a random distribution at test time and then do the Bayesian model averaging. And the idea is that if you do that, then the Bayesian model averaging will kind of diverge on the samples, which are not seen during training, and that's useful for OD detection. Yeah, this is basically showing that you can do BMA with the dropout. So here the pro is that dropout is something that people used to do quite frequently in the past. So the argument here is that you actually do Bayesian machine learning for free. That's really great. But the con is that you've seen this figure before, right? Monte Carlo dropout in practice does not work. There are so many accounts saying that Monte Carlo dropout does not work. I had like personal connections who tried this out and then said, no, it's not working. And then people saying, yeah, I should try it. And then I tried it and it doesn't work at all. So it doesn't work. So that was it for the Monte Carlo dropout. It's a clever idea of kind of having a new perspective on what we are already doing and saying, yeah, we are actually doing something Bayesian here. So I find it, again, quite typical for Bayesian machine learning. You come up with some fancier theory, but eventually if you look at what they do in practice, it's not too different from what people are already doing. So that leads to me the thought whether there is any creative new ways of training new kinds of sets of models, right? It's not my thought, but some other people have trained a different, like qualitatively different type of sets of models, like a curve in the parameter space. A curve is also set. It doesn't have any volume in the space, but still contains an infinite number of possibilities. So the question is whether you can train a curve instead of a point or a Gaussian, right, in the parameter space. And this paper shown here is telling you that you can do that. Here, you're seeing the parameter space in the x and y axis. It's going to be millions of parameters, but you're projecting that to a 2D space here. Not projecting, you're just slicing two-dimensional view of the space. And you have 2 points, 2 endpoints, and there is a curve connecting these 2 endpoints. And along the curve, you're going to see low loss values along the way, training loss values. And that's really amazing because actually it turns out that these 2 points are independently trained models. So they are quite far away. If you are training independently, they're going to end up in different basin of convergence, so to say, people say, right? And actually they found the path which is connecting them with low loss value. That kind of means that these are actually not in different basin of convergence, but actually in the same basin of convergence. Okay, so this is also kind of interesting from the perspective of loss landscape. If you train 2 different models independently, there is actually a path connecting these 2 without increasing the loss value at all. To give you kind of a spoiler here, they find that such a curve exists for almost any arbitrary pair of solution in the parameter space. So that kind of means all the solutions are perhaps linked to each other in the parameter space, perhaps for SGD trained solutions. But there have been some follow-up papers saying, if you train the models in a different way, like using Adam optimizer instead of SGD, you still connect these 2 arbitrary solutions. So the insights coming from this is quite strong and also sometimes counterintuitive and very interesting. Okay, so coming back to the point for Bayesian machine learning, you're now training also an infinite number of models using a curve. So now the question is how to train a curve. It's essentially the same story. We're going to model the curve as a parameterized curve where our aim is to train these parameters. And every point on the curve will be treated as a sample from the posterior prediction. At each iteration, we're going to sample from the curve at random and then train that, compute the loss on top of that sample point. And then we are going to backpropagate all the way back to the parameters, encoding the posterior prediction. So let's take a look at how to do that. We have 2 independent models, theta 1 and theta 2, to start with. We introduce a third point, which is a trainable parameter, which has the same dimension as the original parameter space. And this is the basic kind of way to parameterize piecewise linear curve. Introduce a parameter t. So t here means t is a parameter here, but it's not trainable. So t goes from 0 to 1, right? The curve, right? And we dictate that at t equals to 0.5, you hit phi here. Okay, and every point on this line is either 2 times t phi plus 0.5 minus t times theta 1, or t is t below 0.5, and like this for t greater than 0.5. Okay, so this is piecewise linear. How do you sample from this curve? First, you sample from uniform 0, 1 distribution for t. And then your theta at t is essentially obtained by using this formula here. Okay, and you're going to get theta sample. I hope it's clear so far. Yeah. And the training objective here is essentially you're trying to minimize some likelihood function, log likelihood, where the theta is now a sample from this curve. Okay, you sample one theta at a time, and then you compute the log likelihood there, and then you try to backpropagate all the way back to phi here to do the gradient descent for phi. You can rewrite the objective here using reparameterization trick again. So instead of sampling over phi or q phi directly, you're sampling over a uniform distribution. And then based on the formula that we had before, we are computing theta phi of t. And you realize that t is not a parameter to be trained. And the only parameter here to be trained is phi. Theta 1 is constant, theta 2 is constant. So essentially, these two equations are basically linear functions of phi. And it's fully differentiable, of course. And so you can do backpropagation. And yeah, so you can essentially train this with reparameterization trick without any problem. That's it. So by solving this problem, you train a curve. You essentially find the third point, phi. That guarantees that any point lying between theta 1 and phi in the linear segment, these are also solutions. So if you think about it, this is making the training problem infinitely harder by instead of fitting a single point, you're fitting a whole curve, right? But what's really surprising with neural network is that such a hard problem can also be solved, and for many cases. Yeah, exactly. And for inference, you can again sample from the posterior and measure the Bayesian model average of them. Okay. As I mentioned, the surprise is that such a training is possible for a huge number of, for almost any pair of samples here. Yeah, that's interesting. So some people went on to visualize this in a very nice way. So this is essentially the same figure as this one here, but with more resolution and more fancy color bar, right? And 3D visualization. So it's very high dimensional, high resolution image. You can also take a closer look and see there are smaller wriggles. But the point is that between this solution and this solution, there is a kind of deep valley, a curved valley connecting these two solutions. I think they even made a company out of this visualization, Loss Landscape. It's not the same set of authors, but yeah, quite interesting. Okay, so finally, there's another idea of, sorry, please.
So why are we always using this linear kind of curve? Because in theory it would be possible to do a quadratic.
Oh, okay, yeah. Actually, they had two versions. One is linear and the other one is quadratic, as you mentioned. It's called Bezier curve, they call it. Linear curve is not differentiable here, but this function is differentiable here. But the degree of freedom is the same in both cases. You just train the third curve. Yeah. Okay. Yes.
How do you choose the theta 1 and theta 2?
You just train these with different initialization, and you end up with 2 different points, and that's it. Yeah. So depending on how you look at the problem, it could be the problem of connecting 2 given points. That's one perspective. The other perspective is you just want some curve in the space for Bayesian model averaging. And then you train these 2 models at random and start from there.
So whatever 2 points you choose, you will get a curve so that the loss values are close.
Loss values are close or low?
So whatever theta 1 and theta 2 you choose, you will get a region where the loss values in that grid.
Exactly, yeah. So by definition of solution, theta 1 and theta 2 will have low loss, right? But the surprising thing is that you can find the third point, which connects linearly with the other 2 points without increasing loss value. Okay. So the other way to obtain a posterior is by exploiting the randomness in SGD. So this is another story of what you're doing is actually Bayesian, right? So SGD is kind of a Bayesian way of obtaining the parameters in the first place. So if you look at the training of neural network, you typically lower the learning rate towards the end because you first kind of locate yourself in a good basin of convergence, and then within that basin, you want to decrease the learning rate to finally end up with a smaller region where the loss value is consistently lower. If the valley is kind of narrow, then you have to kind of lower the learning rate to reach the solution. But in this case, you do not, you do decrease the learning rate, but you kind of keep some level of learning rate higher than usual for finding the final solution for some time after, let's say, 75% of training. For the last 25%, you just keep the model do some trajectory around the solution. And we treat the trajectory here as samples from the posterior distribution. Okay. This has connections with Monte Carlo Markov chain, where what you're doing is you do some kind of random walk on the space, and after some random walk, your assumption is that you're entering some posterior distribution. And if you sample from this random walk, it's actually equivalent to sampling from the posterior. So that's the whole intuition behind Monte Carlo Markov chain. And what people say is that if you train a network with SGD, it's essentially Monte Carlo Markov chain. So likewise here, you just wait until it ends up with some region where the solution is. And if you just let it wander around that region, and these are representing the posterior pretty well. Okay, so in this case, we are assuming that the posterior is again Gaussian. But how you approximate the Gaussian, estimate the parameters for the Gaussian is very different. Very empirical. You just let the model do this trajectory with the SGD. And you just take the final L checkpoints, theta 1 up to theta L, and then you estimate the mean and variance there. For the variance, we are assuming again that this is a diagonal matrix, covariance matrix. And so the empirical covariance measurement is pretty simple. You just take the average of the individual squared elements, and you subtract the square of the mean. And that's going to give you axis-aligned Gaussian in the parameter space. You're essentially fitting a Gaussian here, right, in the solution space. So this is a version of what they do. It's called stochastic weight averaging. It's essentially saying that if you just take a few final iterations, checkpoint, these are actually giving you quite a bit of information about posterior. Yes? It's hard to say that for sure. Yeah, the models tend to be quite homogeneous if you're considering a very single basin of convergence. But I think their point is that it's still better than a single point. So yeah, to be fair, they don't focus too much on the OOD detection in this case, epistemic uncertainty per se, but they are more focused on obtaining a better mean actually, right? So instead of using the final solution, the argument is that you should actually use the average of the final checkpoints as the final solution, because that's going to lie in a flatter minima region. And when the solution is kind of in the middle of flat minima, then it tends to give you better generalization for test samples. So there they focus a bit more on, but this is another Bayesian framework based on the Monte Carlo Markov chain. And I think it's worth kind of considering this as another way to kind of at least generate a bit of diversity among the member models. Yeah. Okay. So so far we talked about Bayesian approaches. They look principled, right? But eventually they're just reinterpreting what we are already doing, right? They look principled given that all the assumptions they make are true. But the kind of assumptions they make is, first of all, I wish to talk about the second one first. So the posterior family contains the assumed the true posterior. But that's rarely the case, right? And we don't even know how the posterior should look like in practice. So that is, yeah, not true in general. We also need a sensible prior, which does not make the learning infeasible or inefficient. It's infeasible when the true model is outside the support of the prior. It's very inefficient if the prior is encoding the contains the true posterior with very low probability. We are talking about high dimensional space, millions to billions of parameters, and it's really hard to guarantee these criteria. Well, why do we care about being principled, right? Eventually, our interest is to see which samples are lying outside a training domain, training distribution. So if our focus is really about OD detection, we can just find a solution which is meeting the end goal, right? So I'm going to talk about some popular alternative to training an infinite number of models. So that is basically measuring the distance between the data points, right? That's very intuitive, right? If your sample is away from the training samples under some metric, then we say, yeah, the sample is away from the training samples, and so it's OD. It's as simple as that. So here the question is how to measure the distance between the training samples and the test sample of interest. So we can visualize or we can always use penultimate layer of neural network as our favorite feature extractor and measure the Euclidean distance there or cosine similarity distance there. Yeah, so this is a popular technique. And it turns out if you visualize the features in the penultimate space, they tend to cluster not so badly according to the classes, given its classification task. Yeah, it's not always the case. Sometimes, especially if you train with a linear classifier and cross entropy on top, they may not be very well separated in the feature space. But for some other cases, the feature spaces behave super well, and there are very clean clusters like these ones. So color here means class, and this cross means where the test sample is mapped to. If it's mapped to one of the clusters, then we can say, yeah, it's in distribution. When it's away from any of the class clusters, we say it's out of distribution. Yeah. And there are many, many papers around this idea, like these 3 papers. It's not just these 3 papers, actually. But I'm going to talk about one representative technique here. You just feed a Gaussian mixture model in the feature space. Remember, this is not a parameter space. This is feature space now. And this is a discriminative task with finite number of classes. So what you're going to do here is you're going to you're going to estimate the means of each class in the feature space by averaging across all the features contained in the class. And you can also estimate the covariance matrix in the feature space by computing this matrix here. So eventually you're kind of visualizing each class as a Gaussian like this. Your ODNIS score is essentially just likelihood of the test point in the feature space, given this Gaussian mixture model. Yeah, so your Gaussian mixture is the linear sum of all the individual Gaussian likelihood. So it's basically the density function for the Gaussian mixture at a given test point. You're going to estimate the prior likelihood for yi equals to c by just computing the ratio of class C in the test set or training set. And this is just this Gaussian here, Gaussian density here. Yeah, I guess you're all familiar with this formulation. So these are sigma C and mu C. These are estimated from the training samples. Okay. And then you can put a threshold on this final value here to make a decision whether that's OD or not. That seems to work well in practice, although there is a small caveat that they also do some feature regularization, like spectral normalization. But apart from that, what they do is they just train the network and look at the final layer features, penultimate layer features, and obtain clusters, and then compute the density, GMM density. And that gives you, for example, 91% OROC score for the detection of tiny ImageNet against the CIFAR data, CIFAR 10 or CIFAR 100, which is slightly better than 5 ensemble for deep ensemble. The advantage is that it's much cheaper and more, it's much cheaper basically for training and for testing. And there are also other complex methodologies like energy-based, DUQ, or SNGP. You don't need to know what these are. But these simple methodologies give you better scores. So why not use that in practice, right? Oh, okay. So that's actually it for today.